Well, thanks very much for the introduction. It's very nice to be back. So I'm here to obviously tell you about some frequentist estimation for this particular bivariate meta-analysis model. There's this joint work with some collaborators. I formed a group working on this. I've actually written down all their names so I don't forget anybody, because I'm getting a bit older and forgetful these days. But this project does involve Mike Sweeting, who some of you will know, who used to work here as well, who's also a director of statistical science, I believe, in the same group as myself. Robbie Van Eyck, who visited me actually during my time in the unit. Sylvia Ulskiewicz, I hope I'm saying that name correctly, at the University of Leicester. Keith Abrams, who I think is at the University of Warwick now, and Wolfgang Vieckbauer, who amongst other things is author of the Metaphor package. So this is the sort of super group that I've formed to work on this. So very pleased to be able to present this. I think it's a nice mix of the sort of work I did in the unit. It's got bivariate meta-analysis in the title, which is something I did a lot of work on in the unit. But since joining AstraZeneca, I've done a lot of work on surrogate outcomes. So it's sort of quite a nice mix of sort of old influences and new influences, if you like. And I think I've got some nice material to show you, and if I do say so myself, and a bit of a sneak preview. So the work is in mature form, and so we're hoping to make a paper submission next year. I think this is the first time I've presented it outside AstraZeneca. I have been presented this internally at AstraZeneca. So yeah, hopefully we'll be submitting this work to a journal. I think we've thought about the biometrical journal, something like that type of journal anyway. But I must start with some caveats. This is all work in progress. We do need to do a coding QC and things like that, but I did do a little coding QC myself and it looked good, so I'm feeling confident. But all the numerical results, things are subject to change, subject to coding review. That's the thing about showing you some work in progress, if you like. It's not published yet. So the good side is you get to see something that you wouldn't otherwise get to see other way. On the other hand, it's not quite as finished as it might be. So you've still got a chance to influence the methodology. You might come up with some ideas or so on. Okay, so we're going to start with section 1, a really basic introduction to surrogacy, really. No equations and maths in this one, just to set this first section, just to kind of set the scene, to give you an idea of what I'm talking about. Okay, so I'm going to start with Wikipedia. Let's start really straightforward. Okay. So this is all drawn from Wikipedia, which might have been edited since I produced these. I put these slides together about 10-15 days ago. How quickly does Wikipedia get updated? I don't know. But in the context of clinical trials, a surrogate endpoint, a surrogate marker, is a measure of effect that may correlate with the real clinical endpoint of interest. I know a lot of you know this already. Good reminder, or just to familiarise some people. So we've got a real outcome that we're really interested in. But for some reason, we prefer to use a surrogate outcome instead of it. And there are all sorts of reasons why we might want to find an excuse or a reason for using a surrogate endpoint, an alternative endpoint, rather than the one that's of real interest. Might be cheaper, might be faster. Patients might like it better, might be less invasive. There are all sorts of different reasons for why we might be motivated to want to use a surrogate endpoint. And so your second bullet point here is using the primary endpoint for whatever reason is difficult to kind of measure for one reason or another, and not nice to measure for something like that. And regulatory agencies will often accept evidence from clinical trials that show clinical benefit to surrogate markers, and sort of trusting a little bit, if you like, that's going to translate to the outcome of real interest. So another entry not from the Wikipedia is that a common thing is that primary endpoints may take a long time to present. So often the surrogate is something you get quicker, faster than the real outcome of interest. There's a nice technical support document that's appeared fairly recently. It might be 21 or 22, something like that, but on multivariate meta-analysis and surrogates. And there's just a few quotes from the nice technical support document that you can read for yourselves. But the last one is particularly important from my part of the world. We're often I'm interested in cancer treatments. I work in the oncology biometrics group, so we're interested in overall survival, whereas other outcomes like progression-free survival could potentially be used as a surrogate. We'll have a little think about why we might want to do that in a moment. Okay. So I've got a couple of examples just to kind of just show some results, just to motivate things. This is a bit of a toy example just to serve as an illustration. It's a bit of an opportunity sample from quite an old Cochrane review. The reasons for us wanting to use this as an example will become clearer. But we've got 6 pairs of log hazard ratios for the first 3 main analyses from a Cochrane review. The Cochrane reviews detail there on the left-hand side. But on the x-axis, I've got log hazard ratio progression-free survival. On the vertical axis, I've got log hazard ratio overall survival, and quite a strong correlation there. So there's a little on hindsight, I could have made these points a bit bigger, but no, there was a little point. There are 6 of them, and it kind of looks sort of promising in a way, doesn't it? That perhaps the x-axis is a reasonable surrogate for the y. You know, it's quite strongly correlated. We'll see a line of best fit going through there. Looks like a potential surrogate, but the idea of the statistical modelling it's going to follow is going to be a bit more precise than just sort of looking at things through by eye. But any thoughts? Is progression-free survival a reasonable surrogate for overall survival? Here we're interested. Normally we're interested in are the treatment effects reasonable surrogates. There are other types of surrogacy, like a prognostic level, individual level, but usually we're interested to do the main results, the main estimates to translate for the surrogate. Probably going to need more evidence than we've got here. That's probably what we're going to find, but we'll do this example. We'll have a look at this example. This is a much more complicated example from a recent publication from a group who very kindly put their data available online, so I was able to put it into a spreadsheet. So we've got here quite a lot of studies. I forget how many, it's 40 or so, I think. They do, oh, thank you, Sean. They do subdivide them a little bit by type, is it chemotherapy and comparison, or immunotherapies here. I'm just going to analyse all the data. It's one of the analyses they did. Here we've got objective response rate log odds ratio of the x-axis, and so we've got a log hazard ratio on the vertical axis. So there is the directional effect is the right one, if you like, because stating the very obvious, the true effect sizes have opposite directions in terms of indicating efficacy. But again, this looks reasonably promising, I would say, for surrogate. Not perfect, of course, a bit of scatter there, and a bit more sort of variation around a line, but doesn't look unpromising, perhaps as using the x-axis as a surrogate for the y, I suppose. So just to finish this first section. Oh yes, please, Brian. Yes.
The odds ratio. Over what time scale were you measuring? Is it over the same time scale as the hazard ratio?
You know, I'd have to check. I'd have to go back to the original source. I'm not sure off the top of my. So there it is. Look, it's let's got the title there. But we'd have to go back to the original source. Sorry about that. I don't know off the top of my head. Good question. And this is often a really important issue, isn't it, for interpreting these things? Yeah, not sure. Better just say I'm not sure. So what are the possible motivations for using progression-free survival as a surrogate for overall survival, the hazard ratios? So I think there are at least 3 reasons. But just opportunity, if anybody feels brave, any thoughts? Or I'm happy to answer my own question in the moment, by the way.
Well, it's going to be faster to measure because you don't have to.
More powerful.
Faster is a good one. I like that one. So we're getting treatments to patients faster. These are cancer patients. They need the treatment now because it's serious business. So that's one. So thinking from the patient's point of view, we've got a I would say responsibility to get treatments to patients quickly, if they should be receiving them, of course. Any others?
Yeah.
Higher event rate, proceed. That's another one. I hadn't thought of that one actually, but higher event rate, more mature data. Yeah, that's similar to Brian's actually. So there's 4 now, I think. Yeah.
But shrinking the tumor is probably saving lives.
Yes. Okay. So you might genuinely be more interested. Yes. Okay. So it might be a key outcome in its own right, rather than necessarily a surrogate. Yes, that's great. We're getting more all the time. Great. Yeah. One is cost, by the way. It's cheaper. That's
Why is it cheaper?
time is money. Sorry. Yeah.
So all these they're intimately related, right?
They are really. Yeah. Yeah. And the last one is that people on oncology trials don't stay on the same treatment, particularly after the treatment progresses. So the progression-free survival data is often a sort of what word kind of less intercurrent events, less sort of treatment switching, so it often gives you a sort of a less sort of diluted bias, whatever you want to, for all these subsequent treatments. Yeah, it's not true, by the way, the progression-free survival data is completely free of all that sort of stuff. Let me tell you, it's not, but it's much more free of those sorts of things. It might actually give you, even though it's your surrogate endpoint, you know, there's some big advantages there as well. That's something I do a lot of work on.
It's also other causes of death that might be affecting overall survival in some types of cancer.
True, that's true. Yeah, that's true. Yeah. Great. So I see you're on board with this. We've got lots of reasons for why, lots of which I hadn't thought of. I've got at least three. I've got three of them, but we've got 6 or 7 there, I think, which is fantastic. Okay, so we're going to move on to statistical modelling now. Okay. By the way, how long would you like me to talk for, Sean? Would you like me to leave some time? I'm not sure about
Maybe a total of 45 to 50 minutes.
perfect. Yeah, that's kind of what I got in mind. But just I'm reasonably on track. I'm about 10, 15 minutes in. I've done the sort of, it gets heavier now. Okay, there's some equations and maths and things that is going to start appearing. So when I first came to this sort of area, I was really quite sort of, as often I'm coming to an area of statistics, quite bewildered and trying to understand what's going on. This paper on the left-hand side by Sylvie Busquets et al. I think it's a really, really nice introduction to good statistical methodology in this area. So if what I'm saying sounds interesting, you'd like to find out more, definitely recommend studying this. Also, the nice technical support document I've already mentioned is good. I've just put section 3.2 here, which is the model we're focusing on today. Section 3.2, the meta-analysis by Daniels and Hughes, is mentioned there, amongst other methods as well. Okay. And the other key paper, I suppose, is the one on the right-hand side, meta-analysis for the evaluation of surrogate markers, the stats in meta paper. This is where the Daniels and Hughes model started, I think published in 97. Yeah, so that's what it says. Yeah, got that right. So been around for a little while. And so that's good reading as well. This. So I think, as I say on the next slide. Oh, so I need to read. Perhaps I need to press the screen again.
Oh, yes.
Sorry about that. So today we're focusing on the Daniels and Hughes model. We're not going to try and do a bit. We recognise this is only one approach. It is gaining traction. It's becoming quite standard. But we're focusing on this because I think it's interesting. Seems to be popular. I've got some stuff to tell you about this. So please do not infer that I'm promoting this approach or other possibilities. It's simply the method I would like to talk to you about today, because I feel as though I've got some interesting stuff on this for you. Okay, so finally some statistical modelling. Okay, so we begin with a within study model for the ith study. So what we're going to have pairs of estimates. So I'm going to call my pairs of estimates model because we've got theta I hat and gamma I hat. Okay, so the gamma I hat is going to be the x-axis and theta I hat is going to be the y-axis. Theta hat I is the estimate of the for the real outcome of interest, those log hazard for overall survival, and the gamma I hat are going to be the potential surrogate mark. And these are the things that are on those plots, by the way. And you saw 6 of them. You've seen 6 of those already. Little black dots on that, and you saw I think 40 odd of them on the. That's what they are. Okay, and so what we assume is these estimates are normally distributed around the study specific true values, and with a within study covariance matrix that we will treat as fixed and known. We can get these sort of the confidence intervals. Getting rho is often quite difficult. We'll come back to that. How do we know the correlation between two? That's often the Achilles heel of these types of methods. I always want to put condition on theta I hat and gamma I hat if they're treated as random variables, but people don't always do that. So this offends me slightly. I've been told by some of my co-authors just to relax on that a little bit, because we'll be treating theta, as you'll see, we're treating the theta I as random, but the gamma I is fixed, so it gets a little bit nuanced here. But I really desperately kind of want to put a given the random variables in the mean when they're random variables. I was sort of raised to do that, but we're not doing that. But this is just a perfectly standard bivariate within study model that's used in bivariate meta-analyses, standard bivariate meta-analysis, very, very standard thing. It's really the next slide, the between study model, that defines the Daniels and Hughes model. So we define the between studies model for the I study using this regression. We model theta I, the true underlying value for the true outcome of interest, given the true value for surrogate, and we assume a linear regression on those on the true values. So it's just, I know you got this, because it's not a regression as most people think on those theta I hats you saw on the plots on the true underlying value. So it's a more subtle sort of, I know that's a very obvious thing to people who are statistically sophisticated like us, but it's just worth it's a slightly more subtle thing than people sometimes realise straight away. But this explains how the true study effects vary randomly across the studies. It's telling you how the true study effect of one of them varies randomly given the other one. But this is unusual because I spent half a career assuming that theta I and gamma I is bivariate normal. That would be the standard bivariate random effects meta-analysis. So I quite like stuff like this. I don't know when I'm sort of trying to do research, I like stuff that's different to what I've seen. So I've got something new to try and work on. But at the same time, for a guy like me, it's quite comforting to have something that's quite close to something I've worked on before. So I feel that some of the tricks and things I know might be useful. So I'm not having to sort of just go back to sort of the very beginning when trying to sort of study this new model. So these two models imply a marginal model. And this marginal model is in Daniels and Hughes paper, and you can work this out using the usual sort of conditional expectations and total covariance variance matrix. So I'm not going to work through it. And we now have three main parameters to estimate. We have an alpha, a beta, and a tau squared. And we have lots of gamma i's, the mean for the surrogate, but there you've got the bullet point, lots of nuisance parameters to estimate. Now, Daniels and Hughes, and I think pretty much everybody else, but not today, estimate all these parameters using a Bayesian framework.
Can I ask another question?
Yeah,
Isn't the rule,
I think Simon's got one next, but go on.
isn't the rule also important?
So I did say, we'll come back to that. So the row is going to be treated as a fixed and known, but we are going to have to come up with some strategies for dealing with that. And I'll show you two of them when we come back to the
The
example.
only reason I ask because you're interested in it being a surrogate outcome. So don't you want to know about the correlation?
It turns out to be really important, but no, according to this, no, it's what we're really interested is the between studies regression, and this Daniels and Hughes do just. So actually, it's interesting. This turns out to be a crucial point, and it turns out from frequentist estimation, the row turned out to be really important. But the way the go is that no, these are the parameters that we're interested in. Sorry, Simon, but Brian just beat you to it. Did you have the same question or?
No, I think you might answer it in the next slide. I'll be quiet.
Oh, okay. Well, okay. Well, let's see if I do or see if I don't. So today we were interested to see what happens if we just attempt some frequentist estimation. I just think there are pros and cons to both approaches. I'm not, I'm sort of fairly neutral. Okay, so how do we suggest surrogacy in practice? So is this between study model that the people want to use, the model for the for the true effects? And alpha equals 0 is indicative of a good surrogate, because you've got no treatment effect on the surrogate, that should correspond to no treatment effect for the outcome of interest. Beta not equal 0 is suggests a good surrogate. And if the same direction effects mean the same thing, which is true for the first example, not the second, beta positive would be a good thing. Beta negative for the second example would be a good thing. But we do not require, this is something I wondered, we do not require beta equals 1. It'd be very important for the interpretation of the surrogate and what you're going to get to know what that value of beta is. But if you insist beta equals 1, you're kind of insisting that the tantamount being the same thing, and that's asking too much of a surrogate. So it's obviously crucial to know if it's something like 10 or 15, you want to know how your estimates are going to translate in terms of each other. But yeah, you get the idea. Okay. And finally, we want tau squared to be 0 or small. So there's most of the variation in the true effects of the true outcome is explained by the surrogate. So these are the criteria. It is a bit of an open question of how far you sort of deviate from, how relaxed can you be? I think my position as a statistician, we should try and be strict on all three of these things. I think we should ask a lot from our surrogates. And my view, personally, is if any one of those three things is not yet, so the old song that 2 out of 3 ain't bad. I don't think that's good enough. I think we should insist upon all three of them. But exactly how, it as usually gets down to interpretations. Well, how relaxed you're going to be. But I do know what an ideal surrogate looks like. And this is just a jolly little picture I stole from the internet. Just I thought it just made an otherwise boring slide look a bit more interesting. Showing the hi, Sean.
No, you say alpha equals 0 is means it's a good surrogate and corresponds to no treatment effect. That's no treatment effect on average over trials, right? Because in some trials there could be a treatment effect.
Yeah, if tau squared's more than 0, yeah, you get that line wouldn't go exactly. It's on the true effects, isn't it? So we're interested. So if tau squared was 0, you would have a perfect straight line for the true effects. But I think that yes, I think that's the role of tau squared coming in there, sort of monkeying around there and saying that yes, it's on average. I think so. It's a good question. Just pause for a moment because I see people seem to have gone into deep think.
Yeah, I'm wondering. The treatment effect in the ith trial is theta I.
Yes.
So presumably that means that in the population from which the ith trial participants are recruited, there is a treatment effect theta I. So in some populations there's a treatment effect, and in other populations there isn't a treatment effect. Is that what this
I think
means?
that's what the tall squared allows to happen on. That's the on average. And if tall squared is 0, then you'll be saying, well, the true effect that it lies upon a perfect straight line.
Yeah.
Actually, if alpha was equal to 0, it'd be for all trials. I think so. I'm thinking about that. I'm having to think about this on the spot. So I'm thinking about this more deeply than I probably have done before. Rather embarrassing. I'd rather just taken it as these are. Yeah, I think that's the role of. I think that's the role of tall squared. Usually tall squares in meta-analysis, actually between study variance parameter that says the studies are different. If there's no tall square, they're the same. So I think I'm pretty sure I'm right.
Can I ask about how does this link with Prentice's definition of surrogate outcomes?
That's a great question. That's a big question, and I would have to think. I'd have to think quite hard about it. Maybe we could come back. That's a yeah. So obviously that is a really important consideration, and I think that's That's just part of that one for now. I'm not. Hopefully, other people in the audience can. Caffey's going to answer it. He's got his hand up.
No, I'm just thinking that I guess this is a bit context dependent. So it makes a difference if you're talking about a drug versus placebo or a drug versus another drug.
Yes.
So if you have no efficacy on progression-free survival, then you probably have no efficacy. If you have absolutely 0 efficacy on PFS, you probably have 0 efficacy for OS. But if you're comparing with another treatment, it could very well be that you have a positive effect on one and a negative on another. Then the variability makes more sense. But of course, it could be that the variability is kind of dependent on how far you are away from 0.
Yeah.
And then if you're shifting from one class of treatments to another class of treatments, so if this is working great for one class of drugs, it may not work for another class of drugs, or it could definitely not work for changing treatment behaviors or guidance or having surgery.
So one thing, so this is Cafe Berman, by the way, people don't. So we've got 2 AstraZeneca people in the room. So Cafe is a senior science director at AstraZeneca. So I'm not completely surrounded by MRC biases. You've got 2 for the price of 1 today. But the key word that the Cafe mentioned there is that the treatment effect. So I guarantee that temperature in Fahrenheit is a perfect surrogate for temperature in Celsius in terms of an absolute measure. But a treatment effect for Celsius, a treatment effect for Fahrenheit, if you've got 0 for one, it should be 0 for the other. So the alpha equals 0 thing is crucial because we're talking about treatment effects. Can I keep going? Is that okay? Because I've got loads of great stuff. I've got loads more. It's really great. But let me keep going. What do you think? Would that be okay? You're going to put me down for a moment. Okay, for a moment. All right. Let's move on to some problems for frequentist estimation, because this is where I started with this, I suppose. So what are the problems for frequentist estimation? Well, first of all, it's a non-linear regression. Now, I remember finding it quite shocking that non-linear regressions is non-linear in the parameters, not in the. I remember very basically, a squared term, alpha beta plus gamma x squared, and that was called a linear regression, but it's got a squared term in it. But you've got 2 parameters. So I keep moving across that. I hope this is okay, but we've got 2 parameters there. I can't help but make a point that are multiplied together. So it's a non-linear model. So that's a fun thing to play with from a frequentist point of view, because much statistical theory does not apply, like restricted maximum likely estimate, which is our usual kind of go-to. There are a lot of nuisance parameters to estimate. So for every single study, I've got to estimate a separate gamma I, and the number of nuisance parameters increases at the same rate of number of studies as the same rate of number of studies increases. And this we know causes problems for maximum likely estimation of variance components. I think that's the Neyman Scott paradox, which isn't really a paradox, I would say, but I think it still goes. So we really do. The main concern, I think, is that we'll have the maximum likely estimates of tall squared, and I want to work with maximum likely base type methods. So people who know more. I'm going to spend a lot of time looking at methods at the moment and all sorts of different estimation methods. I want to stick with maximum likelihood today. All right, we know maximum likely estimate will be badly biased now. I think method at the moment is really going to struggle with a non-linear model. So the Bayesian estimation gets a lot of special dispensation from all these sorts of things, of course, but these are a problem from a frequentist point of view. Now, I started doing some simulation study work, and I have to thank Wolfgang Viekbauer for this. He actually very kindly sent me some codes, which I think I could have had the wit to do, to write down a function does the likelihood maximize, but Wolfgang is much better than I do, much faster. He very kindly sent me some codes, which is much better than mine. So I started doing some simulation study, work, just playing around in R, not working in any sort of structured way, just doing some simulation studies. And I found that sometimes estimates of tau squared are very badly biased out, which is kind of what I was expecting. But other times, they weren't. And there seemed to be no rhyme or reason to this. And I found this quite, well, disconcerting, upsetting. I don't know if it's for you, but I take this stuff quite personally, I suppose. The computer's doing this and now it's doing, I've hardly changed anything very much. And so I'm more upset when there isn't downward bias because that's what I was expecting, but it seems to bounce around all over the place. But I wasn't working in a structured way, I have to admit. I was just, in the statistical, that's how I tend to work anyway, just playing around in R. So I thought maybe this is a problem for the numerical optimization, but maybe numerical optimization methods are struggling in some settings. Because this is an issue when assessing surrogacy, when interpreting the parameters. Well, tau squared is one of the key parameters. And if you underestimate tau squared, you're going to underestimate your confidence intervals for alpha and beta because you're underestimating variance components. And so is there a mathematical reason? Is there a numerical reason? I actually need to do this mathematically because I don't trust the optimizer. I have to say I noticed the Nelder-Mead method often got stuck, and the quasi-Newton-Raphson thing, the BFGS thing in R seemed to do a lot better quite a lot. So I thought I think there's something numerical, or maybe there's something deeper. I did get a little bit obsessed with this actually. This was sort of around Christmas time, sort of last year. I did get quite obsessed with it. Wanted to understand why this is. So I started by deriving some maximum likelihood estimating equations. So going back to trying to do some maths. So got the marginal model. Here's my marginal model again. When differentiating the likelihood function with respect to gamma I, only the bivariate normal from the I study contributes to the log likelihood, should we say. So this is just the contribution. So I can take away the alpha from the model here. So we're starting to get into some statistics now. So I can move this into a standard sort of least squares model now. Here, can I just move over this side? These are my estimates. I've got an alpha here. This is just my design matrix. This is a weighted sort of linear regression model. What I should do is differentiate the log likelihood, substitute in the parameter estimates and set to 0. If I substitute in the parameter estimates, I know what's going to give me the maximum log likelihood because it's just a weighted least squares regression problem. There are standard formulae for giving me that. So I'm actually not going to show you because I don't need this for today. In the paper we do derive, but this estimating equation, by the way, for gamma I has all the other parameters on the unknowns on the other side. It's that sort of estimating equation. It's not a closed form estimating equation. This is sort of one you can use to iterate around. It's one of those that sort of estimating equation. Don't think closed form things. So I was quite pleased with that. So I've got some estimating for all the gamma I's. So I've got that. I don't know why I feel more comfortable on this side of the room. I don't know why. Maybe because I started here. I don't know why. I'm going to go back here. I can't explain why that is, but I feel happier here. Okay, so I've got estimating equations for the gamma, all the true gamma I, and so I just need alpha, beta, and tau squared. I've got estimating equations. Okay, so then I'm kind of back in control, and I think I need to click the screen again. Sorry about this. This seems to be a recurring. Okay. Estimating equations for alpha and beta can be derived. So we've got a marginal model. This is equivalent to, so what I've done is I've sort of done the model for the gamma I hat and then the model for theta I hat given gamma I hat as a linear regression, because you have to work. There's a Wikipedia page, by the way, I find very using a lot of Wikipedia for the properties of a bivariate normal distribution, the mean and variance of the conditional distribution. You just work through this is what you get. And this is just a standard, again, a standard sort of model, isn't it? This guy here, this mess here, that's just an offset. These are weights, alpha and beta in there as well. So again, if I was doing this properly, I would differentiate the log likelihood. It's only the conditional terms from the theta given gamma I had that contribute. So if I differentiate the log likelihood to 0, substitute the parameter estimate and work out what would give me the maximum likelihood estimates from that. But I can sort of cheat, and by putting the parameter estimates first, think, well, this is just a standard model, so it must satisfy the standard model, estimating equations for a standard linear model, and so I can get estimating equations for alpha beta as well. I'm not going to show you those equations either, but I've got them and I've written them down in my paper and stuff like that. An estimating equation for tau square can be derived. This is where things get more important, and it's only the conditional model again, remember that the tau squared appears. So it's the same trick again. It's just the conditional part. Differentiate as same for alpha and beta. Differentiate the log light with respect to tau squared. Only terms from the conditional model survive. We cannot turn this into an estimating equations type of thing. It is now a standard non-standard sort of meta-analysis type of thing. Luckily, the mathematics is so easy that even I can do it. Luckily, the mathematics is so similar to standard meta regression models. It's already been done before, practically, as I'll show you. So, luckily, because I've been working in meta-analysis for quite a long time now, I know how to do this. And so, what we do is we write the conditional mean of theta I given gamma I hat as that mess there, and this as another sort of conditional within study variance, if you like. We then get this as the margin. I'm making it look more like this thing here now looks much more like a standard meta regression model. I've got my tau squared here, I've got my linear predictor here, I've got my within study variance here. I've done the usual trick of reparameterizing, if you like, saying that's that and that's that, and making it look like a standard meta regression model. And we can also write, we can also obtain the maximum likely estimation equation for the conditional mean of gamma I hat, theta I hat given gamma I hat. And then the resulting estimating equation is this mess here. That's what pops out. But there's a paper Simon Thompson published, some people know Simon Thompson, Stephen Sharp, I think they published this 20 years ago, something like that. They come up with this iterative estimating equation. It's exactly the same thing, really. They've got a linear predictor in here. Well, I've got a more complicated, it's got estimates there. Looks like I've got estimates there. Got to take away within study variance. Mine's a conditional one. It's basically exactly the same. Now I'm sort of saying it's a new estimating equation, but it's all been done before. Okay. So I know I've got it right because it's exactly analogous to that. I've sort of re-expressed it. So what it is, if you like, what we're doing is we're taking some residuals here from the theta I've given minus the conditional mean. We're taking away conditional within study variance, sort of a weighted average of those. It is a fairly sort of intuitive sort of form. This is the only of the estimating equation I'm showing for you, but you can see that you've got tau squared on the left hand side, you've got other things on the right hand side, like you've got the tau squared unknown, the mu I hat is a function of all the other, so you have got all the, it's what I said it was. It's not a closed form thing. It's a it's one of those sort of iterative sort of estimating equations. Okay, so I've got my estimating equations. So I'm feeling happier now. I'm actually doing the work, sort of not playing around in R, doing things numerically. I'm doing the maths. Yeah. So we can do useful things with the estimating equations. We could use the estimating equations to obtain the maximum likely estimate. So we could come with this. I think it's what people did back in the day. I don't really want to do that because I've got Optim. I could but what I can do is use them to check the optimizers of word. So what I can do is I can plug all the estimates into my estimating equations and check everything is satisfied. So I know there's not numerical, and I know Optim sometimes says conversion code is 0 or 1, but it doesn't always get it right. Particularly the Nelda Mead one, but was getting stuck with this. So I now know that it's not the case that there's numerical problems for some of those settings. That's not it. So it is something deeper. What I then try to do is let's try and derive an estimation for tau squared that tries to eliminate the bias in it. That's the next step. So a bias adjusting estimating equation has been derived. So this is just a reminder of my estimating equation and the conditional model. What I'm going to do now, and please don't laugh too loudly, I'm going to pretend for a moment that all parameters were known, that tau squared was known, alpha, beta, the whole bang shoot was known. Then the law of total expectation shows that the expectation of tau squared hat is tau squared. And that's actually quite easy to show because the expectation of this guy here, conditional, is the variance, which is that there. So when I work out the expectation, so I have to work out the expectation, the conditional thing, the sort of the tower thing, or whatever people take the expectation given the surrogate, and then take the expectation around that thing. So when you take the conditional expectation, this thing here becomes a tau squared plus 3i squared taken away, and the whole thing collapses. You just at a tau square. If you're nodding, actually, you can actually see it in your mind's eye. You're just that good. So the key result required for that is that I'm using the true mu I here. But this confirms that maximum likelihood estimation, its heart is in the right place. Right, it's trying. And something I learned from mentors in the past, I could name them, but I won't name them. People have influenced me anyway. Have told me maximum likelihood estimating equations often provide a really good starting point, even in situations where the maximum likelihood, the criteria you need from the problem doesn't work. Like here, the number of parameters increasing at the same rate as the number of studies. So yeah, right. So what I decided to do is to do the next worst thing. The next. I was doing the worst thing. I'm going in the right direction. I'm going to ignore uncertainty in alpha hat, beta hat, and tau squared. Ignore that uncertainty. So I know from Neyman Scott, it's the gamma i's that's causing the problems. So what I did is I'm going to treat them as if they're fixed constants. And that's kind of okay asymptotically, because I get more information about alpha and beta hat as the sample size increases. And any downward bias in tau squared is going to help me because it's all just linear models really, and the variance just increases. Yeah, all the biases are going to come out okay, just inflating variance, I think. All right, so if I treat them as fixed, I think. But what we're not going to do is treat the gamma I hat MLE. They're the estimates from my estimating equation, the maximum likelihood from the whole meta-analysis model. I'm not going to treat the gamma hat MLE as known. So this is where things do get a bit complicated with the gamma I hat for me. Because first of all, I've got the true gamma I hat. Sorry, first of all, I've got the true gamma I. Then I've got the study specific gamma I hat, the estimate from that study. And then I've got the model based one that's kind of assuming exchangeability and all this. People know, you know all this. But so I'm using this to distinguish between what I get from the meta-analysis model for estimating gamma I hat and the data point that's going in that was the horizontal sort of, okay. And so remember that this estimate of the gamma hat MLE is from a weighted regression where theta I hat and gamma I hat are the outcome data. So obviously this is a linear combination. Of course, that's what linear regression is all about. So even I remember that. And so if that's a linear combination, so is this conditional mean a linear combination? Because we've got this thing here, it's a linear combination. There's other terms as well. I'm treating as fixed. And no, all I've got to do is sit and do fiddly maths and work out what AI, BI, and CI are in terms of all the algebraic mess. And I can work out what this linear combination is, you see. And these coefficients, AI, BI, and CI, are functions of alpha hat, beta hat, and tau squared hat. But remember, we are treating these as fixed constants. So the idealized result that makes the maximum likelihood estimate unbiased is this, with the mu I, the conditional mean of theta I hat given gamma I hat. So the conditional variance is given by the phi equals tau squared. The less idealized result, ignoring parameter uncertainty alpha, beta, and tau squared, but not the gamma I hat, is this result here. And you can just work this through. Alpha and C are AI and CI are treated as fixed. So I've got a BI floating around. You can just work this through. This is almost sort of A-level type maths. If A is a constant, the C is a constant, you can get. So if I can work out what that B is, actually it doesn't matter. I've worked out what A, B, and C are. I've got algebraic expressions, but I've checked them numerically. But I could get A and C wrong. It doesn't matter for the calculation. I need to know what that BI is. And that's going to be, I've called it B. I thought it was quite nice. A, B, it's called a bias correction term, you see, because these are going to play a role in the bias correction. Just lucky, isn't it? B, it's just A, B, and C, and yeah. Anybody think I put the coefficient in that order just so I've got the B for bias? I wouldn't do a thing like that. Okay, so we're now proposing the following bias adjusted estimator, where instead of taking that sum of squared, we've got a 1 minus BI to minus 2 there. So when you take the expectation through the less idealized result, it pops back down to tau squared again. And so the estimator that uses this estimator can be used in a bias adjusted meta-analysis. It takes tau squared and fixed and known. This is something we often do in meta-analysis approximation. Take the variance components as fixed and known. And very tedious algebra can be used to derive. This took me, I got obsessed with this before Christmas. I came back to derive this after Christmas. I got this expression here in January. And when I saw this expression, I thought, I'm still doing good stuff here. This is nice. Because beta hat is the estimated between studies slope. Remember, that's one of the key parameters on the true effects. And Brian asked, who's run away, but he's come back. Right, hey Brian, you're back. You're coming back to your row I's here. If I divide by delta I, that's the slope from a within study regression. If I just take the within study model and work out the slope from that, using Wikipedia part, if you go to Wikipedia, that's the, so if I just divide by beta, I could divide by beta squared. Well, that's a variance divided by mean squared. That's something. So maybe I should put the beta down here. That's a sort of, people talk that as a variance divided by mean squared. That's some sort of measure of something or other. What the thing he's doing, and I wish I was just a little bit more clever and had better intuition for this, I really do. But what the thing he's doing is comparing the between study slopes and the within study slopes. And when the between study slopes, the within study slopes are the same, the bias correction term makes no difference. That's their estimator, because rho is really an estimate, to go back to Brian's point, and I'm having to use beta here. But when they're very different, these bias correction terms can get pretty big. And remember, this 1 minus bi squared. So the nice thing about the bias correction terms, they're well behaved. They take values in the range 0 and 1. So they're expanding the residuals. Remember, variance components are estimated by residual sums of squares, aren't they? Really, what I'm doing is I'm expanding the coefficient. It was 1 here for the the maximum likelihood. I'm expanding that, and they are well behaved. They're always going to increase the variance, aren't they? I thought this was very, very, very nice. So when I went back to I'm going to talk about five minutes or something like that. Sean, is that okay? Yeah. When I went back to my preliminary simulation work, I couldn't understand what the heck was going on. Luckily, I'd saved a few, not all of them, and I went back and I thought, that one, tau squared, was perfectly well behaved, not much bias, but I'd happened to do it so the within study slopes and the between study slopes are very similar. And then other ones where, the other thing that's in the way, and I was changing all sorts of things, assuming the number of studies. It was only one thing that mattered. It's much simpler than I thought it was. I thought it might depend on the number of studies, tau squared. It's only one criterion that matters. And this, of course, is why maths is great, isn't it? This is why we like maths. So we're doing a proof of concept simulation study, just to and quickly come back to the examples. So this simulation study, just going to do some things quite quickly. 1,000 replications in each setting, 54 settings in total. We just use 20 studies throughout, just a reasonable sample size, not too unrealistic. Within study variance is the same for both outcomes, but varying across the studies. 3 values of tau squared, 3 within study correlations, 3 true betas. And because the 2 variances are the same, when rho I are the same, when rho I equals beta, then those are the settings I would expect maximum likelihood estimation to work absolutely fine. I know I've got it depends upon the estimated slope, not the true slope, but you expect them to be in similar, in good agreement. And 2 values of alpha, not expecting this to make much difference. One good alpha equals 0, good surrogate. 1 alpha is 0.25, bad surrogate. In terms of the beta equals 0, bad surrogate. this sort of thing. 3 values of tau squared 0, good. So some bigger ones are sort of quite bad, I would argue. And so we looked at biases of estimates, biases of some Bayesian estimates, just using a uniform 0.2 prior for tau, because this is what's put in the nice technical support document, seems to be fairly standard. No, I'm not going to try and die on any hills defending that. We all know that is an issue, but it's just to compare it to something Bayesian, looking at the coverage of intervals, with particular interest where beta equals rho, because we know that's when maximum likely estimation should be fine. So I'm just going to flash some sort of simulation study results before your eyes, I suppose. I'm not going to show you, there's no results for alpha because everything for alpha is fine. Maybe show this is the bias for beta in the top left-hand corner. And this is the bottom left, the bias for beta in the settings where beta equals rho, where everything should be fine. That is fine here. Interestingly, in the top left-hand corner, sorry, red is stop, red is bad. That's standard MLE. So red is this. Everything's color coordinated with me because I'm a visual person. So red is kind of, I know maximum likelihood, red's probably bad. Green for go is the adjusted one, and blue's the neutral one for Bayes. Okay, just that's how I think. What's quite interesting is the Bayes bias for beta is absolutely fine when beta was wrong. That's a problem for maximum likely estimation for tau. That's the issue there. It also seems to have a sort of a consequence knock on for the Bayesian analysis in terms of bias for beta. So something I was told early on is that when you've got a problem for one, you've already got a problem for the other. You've got a problem for Bayesian analysis. You've usually got a problem for frequentist analysis. They just manifest themselves in different sort of ways. I've got no explanation for that, but I do know that when the within study between study slopes are different, that affects tau squared. And it does seem to, and it could be dependent upon the prior and the simulation setup, but there is some knock-on effect there. But tau squared, this. So with the Bayesian, I'm getting sort of a positive bias throughout because I had quite a prior that was from 0 to 2, bigger than the values I was using for tau, and the adjusted nicely sorts out the the bias for torque, not perfect, of course, and hardly has any impact when the slopes are the same as one would expect. So it's working kind of as I would expect. And some coverage probabilities as well. Bayesian actually winning this one. So Bayesian kind of loses on the bias for beta, which is important consideration. Don't quite understand that, but the adjusted certainly wins for the coverage of the. Doesn't do anything very much when maximum likely estimation is fine, of course, as you would expect. But look, I mean, we're getting sort of coverage probabilities of 75% for a standard maximum likely analysis. I can improve it to about at least 90%. It's not perfect, of course. I think but I do think the Bayesian would win that one on this particular round at least. And so, yes, some conclusions there. I think bias adjusted estimation does outperform standard maximum likely estimation. No clear winner between a conventional Bayesian analysis and the proposed method. However, torque squared is an important parameter, and I know a lot of my colleagues would prefer not to have to specify priors for that. If they don't have, this is something that happens. People are using these Bayesian methods, and they feel it sort of absolves the analyst of having to make a decision about what prior to use. So it does have a certain sort of appeal there. Very, very quickly, because I'm up to time really, but just to go back to the two examples. So what I've done is I've applied the frequentist method, both adjusted and unadjusted, and the type of Bayesian analysis I've shown you previously to the two examples. So we're going back to the exam. Remember the exam, this was one with six points to begin with. And so what do we get here? Well, for alpha, I sort of positive alpha, but estimate of alpha, but confidence interval includes 0. That doesn't look too bad. Torque squared of 0 frequentist, and that's for both analyses, by the way. So we know the bias adjustment helps to increase the torque square, but it doesn't do enough to increase. That's quite a simple message there. I quite like this example because it is an example where standard maximum likely estimation is fine because the within study slopes and between study slopes turn out to be quite similar. Now the Bayesian, by virtue of its prior for torque squared, does give me a positive torque squared and does give me a wider confidence interval for beta, as Bayesian analysis will. I do think the Bayesian analysis better allows for uncertainty in an example with 6 studies. I'm not going to try and argue the frequentist method better handles the uncertainty in beta. It looks reasonably promising, I would say, for this being a surrogate, because the confidence intervals for alpha include 0, beta, who are the frequentist ones, but not sure about the Bayesian with the uncertainty, beta. Basically, I think it looks promising. My interpretation looks promising so far, but more evidence is needed to get some narrow confidence intervals. What a surprise on the basis of 6 studies. Inconclusive.
What's your credible interval around torque squared?
That's great. I'm dodging that because I don't know how best to do frequentist ones. So I have the Bayesian ones, of course, but I'm just suppressing that for today because that could be the next part. How the best way to get confidence intervals for torque squared. Thank you. Yeah. So I'm playing. I was hoping just to sneak that one past you, but you got me. Okay, so here's then this is the last thing I want to tell you about. So, sorry, no, one thing I should say here is that we take rho I equals 0.5134 studies. The reason why I like this example, there is some published information on one of these studies, and one of my collaborators, Sylvie Busky, which helped with actually know an estimated correlation for this one. It's in the published literature. So let's take a slight leap of faith and assume the correlation is at least similar across all studies. I'll go through frowny faces, it is a bit of an assumption, but this is one strategy. Get some IPD for one study and assume it's sort of indicative of everything else. So that's one way of coming back to the rho issue. Here's the more complicated example. We expect a negative correlation because remember the direction effects of the treatment effects are different. So I've done quite a wide interval, a wide sort of sensitivity analysis. -0.1, -0.3, -0.5, -0.7, -0.9. Yes, I do think the -0.1 and the -0.9 are on the ridiculous side. I think it's the 0.3, the 0.5 and the 0.7 with the minus signs attached to them. But here's the results that you get. And I'll just let you sort of eyeball some of these things a little bit. You're intelligent people. You look at Winton. But one thing I'll just show you is that as this within study slope increases, the standard maximum likely estimation starts to go badly wrong. That's because the within study slopes and the between study slopes start to differ very substantially. But the adjusted maximum likely estimate starts to match the Bayesian one much better. And that's because I'm making the within study slopes now, the correlations of -0.9. Those within study slopes are starting getting really, really big now, much steeper than that line there. Now, although I do think the -0.9 is a bit unrealistic, it's also starting to do its stuff here look quite nicely. Some MLE 0.04 for torque squared, but the Bayesian and the adjusted maximum likelihood, well, they're in sort of perfect agreement. So what do we think about this one as as a surrogate. Well, tau squared kind of looks quite good for me, not zero, but not too much unexplained variation. Beta looks okay. I've got the negative slopes, quite narrow confidence or credible intervals, but there is a bit of a problem with the alpha, isn't there? Really across the board here, really, in that it does look like there's a negative. So if I look at the zero here, it's kind of giving me an intercept here. It's giving me an intercept around about here, which is not something my eye tells me, by the way. I don't know about you. You're that good. I can't see that, but the model is telling me that. Here, it's just down here, and it thinks it's stat sig. So I don't have to wax lyrical about how great statistics is. Now, I did the maths bit, but obviously that's what stats is here for us to do. When human intuition lets us down, that the stats kind of goes in there, takes over a bit. So it does look like we're getting a treatment effect on one and not the other. And depends how relaxed you are about these things, and all the rest. And people might, sort of argue differently, but I think I would stick to my position of wanting all three criteria, and I think that is quite a marked departure. So I'm not convinced about surrogacy here, but I'm not going to make any big statement. I'm not going to make any strong statements. Might contradict what that review said, might to be with official positions and things, but yeah, it looks a little bit suspect from the inset when it's a Daniels and Hughes model. So some conclusions. Some main take-home messages, which I think I'll just let you read there because I'm not up to time. And the main conclusion is good frequentist estimation of the Daniels Hughes bivariate meta-model. You can read that as well. You can do good frequentist estimation of the Daniels Hughes bivariate meta-analysis model, provided you do it my way. or our way. Sorry, that was very that was very Dan said. But there's some take-home messages now. Just let you. You can read those at your leisure. I've got a bit of time for questions, but I think I've overrun a little bit. So thank you.
Thank you, Dan. Do we have any questions? Oscar.
Yeah, very nice talk. Thank you.
Thank you.
I'm not sure I understood this. How would you estimate with real data the correlation, the raw correlation for each study? Let me see if I understood correctly. So could you, for example, for one study, split the data into subsets and see what is the association between hazard ratio? Would that give you an estimated correlation in your model?
Or possibly bootstrapping is a very popular approach, by the way. So that there are algebraic formulas for certain. So if you fit a model this way, and that people have worked on, there is a paper by Way and Higgins that sort of gives lots of formulas for getting some of these correlations. If that correlation doesn't exist, or bootstrapping, which is kind of very close to what you're proposing actually. So bootstrapping is often used to estimate the ROIs. Yeah.
Simon.
So your three criteria.
Mm-hmm. Well,
In that last table, you were kind of assessing them one at a time.
Yes.
You're not thinking of doing them as an omnibus, like all three.
Could do, couldn't you? So I know you mean they say the mic. I don't know if they belong, but that's interesting, isn't it? So alpha and beta, there's a ellipsoid there, isn't there? And tau square is one more difficult. No, I like that. I've not thought of that. People do them one at a time, but that's a nice side. Sorry, I'll let you.
I mean, just as a Bayesian, Bayesian line, I would think about all three simultaneously.
Yeah.
And I would think about how much the three match your criteria. I just wonder, as a frequentist, would you try and do all three at the same time?
I think you could do. You mean alpha and beta are fairly straight. The tau squared one's always quite hard because you don't quite know what you're going to do by profile likelihood, or are you going to do what transformation you use for your wild type stuff. But in print, yeah, I think that's okay. That's I'd not thought of that. People definitely do this one at a time.
You're so thermal that you need to do all three.
Yeah.
I disagree with you. But
You want to do them all at once, but I suppose if you do three things at a time, one of the things might get lost in the mix, mightn't it? I have to think. It's a really clever point. I like that.
You tested in that case, alpha equal to 0, beta not equal to 0, and tau squared equal to 0.
Well, that's a good question as well, because alpha and tau 0, and tau is at the edge of the parameter space, isn't it? Which is one problem. Alpha, the beta, it's not 0, so you just need a bit of thinking through. Maybe there's a reason why people do want it. But I'd never thought of that. So that's actually a new idea to me, Simon. So sorry. Yeah.
I'm sorry, I've forgotten your name, or maybe I didn't even catch your name in the first.
Carl Fredrik Berman.
Carl Fredrik Berman.
Exactly. Yes, in this case, you have objective response. Right? So this means that the tumor is shrinking by more than 30%.
Right.
So you could imagine, I don't think this is the explanation here, but you could imagine a drug not stopping the growth of a tumor and thereby leading to a survival benefit.
Mm-hmm.
So I think in this case you could imagine that you have alpha smaller than 0.
Mm-hmm.
You look at the kind of the mechanism here,
Mm-hmm.
and then you're looking at the odds ratio for objective response rates,
Mm-hmm.
and the objective response rate is typically 0 if you don't give a drug.
Mm-hmm.
So this is probably in the setting, at least when you have some kind of background therapy, and perhaps that will be a slightly different situation.
So just you think you've got an explanation for why it's negative, Kath? I'm just trying to
I
potentially.
I wouldn't dare to say that, but I think in principle you could have, depending on what kind of variables we're talking about, you could have a surrogate. If you don't see anything, you could still have efficacy on survival.
I see.
Whereas if you do see efficacy on objective response rates, you would be pretty certain in some cases that you have some effect on survival. And of course that's complicated because you can have other factors coming in, toxicity, and if you're comparing to different kinds of drugs, then of course one could be better on one and the other on the other. So but I think the main message is that we may need to think carefully about what kind of variables we're talking about.
Mm-hmm.
So are you
Total context.
Are you suggesting that a drug might reduce so progression-free survival? You said something about 40%. You said something about 40%.
Well, I guess that progression-free survival is partly survival.
Mm-hmm.
So I guess that if you don't have toxicity, if you're prolonging the time to the tumor has been growing by 20%, or the patient has been dying, that's probably saying something about when the patient is dying.
Right.
I guess here that if you see objective response rate benefits, so some patients having tumors shrinking very much, more than 5%, that may be a good indication that something is happening and we can at least hope that we have survival benefits. But say that the tumors are not shrinking, but they are not growing, that would also be a benefit, and then you would not see that in objective response rates.
Right. Yes. Okay.
And it could be that you are shrinking by 20%, but not more than 30%.
Yes.
So the context and the variables sometimes will tweak things a bit. So I still think you're right that we would like alpha to be
Okay.
0.
Okay, it's interesting. It's certainly just thinking from a common sense approach, right, which so progression-free survival and overall survival, there's some sort of survival. So it feels more natural, doesn't it? That one could be a surrogate of the other, but some sort of objective response rate, that's something completely different. Just from very simple sort of commonsensical thinking, that's more of a stretch, isn't it? Even the statistics, that's a simpler version of what you said there, Cafe. But absolutely, I'm thinking more hard about this context. Anybody who think I chose these examples, I thought they were nice examples to illustrate my methods on, rather than really thinking about the maybe I should think about it. Oh yeah, you've got me. Yeah. No, okay. It's very interesting. Thanks, Cafe.
Do we have any questions online? And Brian, did you? No. Any questions online? If you have, then either unmute or put something in the chat. Just say that you want to ask a question.
How many people have got online? Do we know how many people are broadcasting today?
Well, it's down to 13 now, but it was more like 25, 30 at one stage.
Okay, I suspect some of them are my co-authors, but that's not bad.
Okay. Yeah.
So I have a question to the audience. You're working on causal inference, some of you are. Yeah. So wouldn't this be nice from a causal inference perspective? And I don't understand causal inference.
You do.
It's always
You're far too modest.
And I guess in this case, it's kind of even more complicated because one thing is, do you have a causal link between the surrogate, the objective response rates, and overall survival? But that's not really the question. The question is something about the treatment. If the treatment is causing an effect on ORR, is that causation causing another causation?
That sounds like a mediation analysis is required of some form. That sounds like a question of mediation. I don't know how you do that with the sort of data that we're talking about here.
You run the individual level.
Also, yeah.
Well, that's a whole other discussion about aggregate data versus individual level data and things. Interestingly, people are often interested in surrogacy at the treatment effect level. So though they'll do an individual level data meta-analysis, they often turn to aggregate level stuff for this type of analysis and conclude this is more important, which seems quite counterintuitive. But that's an individual level data. So that might allow you to do the mediation stuff. Interesting. I thought I've even considered that. So thank you.
So if you had the individual level data, would you get the same answer?
That's a great. So there are the individual level data models that allow you to do both the within trial sort of surrogacy at a sort of prognostic level, and also that have parameters for the trial level, so all in one go, and allow you to do the whole thing. What people often do in practice is they do their individual level data. Maybe including the probably including rather the trial level surrogate, use that to assess that level surrogate. But then when they come to the trial level stuff, they start presenting the aggregate stuff because it's simpler to digest. It's more sort of transparent, and they think it's perfectly adequate to assess. Very strange to me because I spent a lot of time telling people when you're looking at more complicated things, you should make use of the IPD. So they just need to be thinking surrogacy that they'll, for the treatment effect, they'll start going aggregate level. But I don't think there's a strong conventions as to it. I think that there's a lot of analysis methods out there yet, and I think there's a lot of variation in practice. So I wouldn't want to make strong statements about what's done, really.
Okay.
I think we'll end it there then. Thank you very much.
Jeff, me out the building.